start the recording here and share my screen so that we can use our whiteboard. So chapter 5 is all about thermochemistry, which is looking at the chemistry of heat. Okay, so that's what chapter 5 is all about. Hey, Connor, can you mute your microphone? Thank you. Well, it worked for a second. Okay. Well, I think he left us again. Hopefully he'll be able to get that figured out. I know that these connections are tricky. Okay, so again, I will upload all of these notes once we finish, and I'll have this recording, and I'll send you the link for both YouTube and Collaborate. So we're going to look at thermochemistry. Well, we will as soon as my whiteboard starts working. There we go. All right. So thermochemistry is basically the chemistry of heat. And really we kind of extend that to include and energy, because heat being a form of energy, we're going to look at a couple of other forms of energy. So what is energy? Energy, and this is kind of the basic definition for energy. Energy is the capacity to do work and or transfer heat. Okay, so that's energy. To do work or transfer heat. So what is work? Well, work is the energy used to cause an object to move against a force. Okay, so the energy used to cause an object to move against a force, and of course we do work all the time. Okay, when we're vacuuming the floor, when we're walking up and down stairs, we are working. We are using energy to move an object against a force, whether that object is our body, okay, or whether that object is a broom or a vacuum. Okay, now heat is also a form of energy, but it is the energy used to cause the temperature of an object to increase. Okay, so keep in mind, and as you learned from your video, heat and temperature are two totally different things. Temperature is really just a measure of heat. It is not the same thing as heat. Heat is actual energy. Okay. Temperature is really the way that we measure heat. So they are not the same thing. Okay. Now when we look at energy, we have kinetic and potential, and you've learned about kinetic energy and potential energy before. These are kind of standard definitions, but kinetic energy is the energy of motion. So when we are actually doing work, so something is doing work, or we have heat that is being transferred, and we have a formula that we can use to measure kinetic energy. And so kinetic energy, so EK there represents kinetic energy. And kinetic energy is equal to half of the mass of whatever it is that you are moving times the velocity squared. So velocity or speed, okay? And so everything, including all the way down to our atomic level, possess kinetic energy, okay? Unless they are at absolute zero. Remember, absolute zero, 0 degrees Kelvin, or 0 Kelvin, sorry, not degrees. So 0 Kelvin is absolute zero, okay? And that is when all atomic motion stops. So all atoms are going to possess some type of kinetic energy or some level of kinetic energy unless they're at that point where atomic motion stops. Okay, so that is kinetic energy, or the formula for kinetic energy. Okay, and we don't really have completely specific units for this. The kinetic energy is going to take its units from whatever units you're using for mass and your speed. Now, typically, okay, our mass, we're going to put our mass in kilograms because that is our SI unit, okay? And typically, we want to put our speed or our velocity there in meters per second, okay? So that's going to typically be our units that we're going to use, but as long as you put in your units and your total value that you get from working your problem with kinetic energy has all of those units, then I'm okay with that. Okay, so if you have a couple kinetic or one or two kinetic energy problems that you have to work on your assessment, and as long as you put the units in there, then that's okay. I can't hear anything. All right, thanks, Kinley. Okay, so as long as you put those units in there, then I'm okay with that. So if you have mass in pounds and your speed is in miles per hour, as long as you put that in there, as long as you put that your unit is, pounds times mile per hour squared, then I'm okay with that. So just make sure you put your units. Where that becomes important, or where we really look at these units being the SI units, the kilogram and the meters per second, is when we start looking at joules, when we start looking at these formal units, and we'll get there in just a second. So kind of the opposite of kinetic energy is potential energy. And we say that this is stored energy. It's energy that is available to do work or to be in motion, but it's not quite in motion yet. Okay, so it's stored. And your classic example that we always give for this is at the top of page 167. When you're bicycling and you're at the top of a hill and you're not doing anything, you're just sitting there, that's potential energy. Okay. But once you start going down the hill, now you are in motion. And so your kinetic energy is increasing and your potential energy is decreasing. In chemistry, One of the forms of potential energy that we look at is referred to as electrostatic potential energy. Okay, or E sub EL. And this is going to arise from the interactions between charged particles. So basically what we're looking at in terms of chemical bonds. Okay. And we do have a formula for that. Okay, where this K here, it's kind of a weird K. This is a constant. Okay, and it's the proportionality constant. And then the Q1 and Q2, those are our charges on our particles. And then D is the distance. Now, we're not going to work any problems using this formula, but I wanted to provide it for you, that the electrostatic potential energy goes to 0 as your D becomes infinite. So as your D increases, so as the distance becomes greater, then your electrostatic potential energy value becomes closer and closer to 0. So as those particles get further and further apart, then the potential energy between them goes to 0. They can't interact if they're not close enough to interact. So as the distance increases, the value decreases. Okay. So that is what is really happening at the molecular level in terms of potential energy. But like I said, we're not going to do any calculations with that. I did just want to provide it for you. So I mentioned this joule, okay, and it's not spelled like a precious jewel, J-E-W-E-L. This is spelled J-O-U-L-E. It is named after James Joule, who was a British scientist who did a lot of work or a lot of study in heat and work and energy. And so we honored him by naming the SI unit for energy after him. So the joule is the SI, or the international system, basically the metric system for energy. And it's the one that we're going to use. And 1 joule is equal to 1 kilogram times meter squared over second squared. Okay. So 1 kilogram times meter squared divided by second squared is equal to 1 joule. And this is derived from that formula for kinetic energy. So kinetic energy can be expressed in joules when we use these specific units, because we're going to get kilogram from our mass times meter squared second squared, because we're going to square our velocity. So we can use the unit of joule as long as we're using kilogram and meters per second in our kinetic energy formula. And so that's where these units came from. Okay, so they were derived from that formula. Okay, and sometimes we will see energy expressed in calories, and this is a non-SI unit. So calories is not an SI unit, but it's something that's familiar to most of us. Most of us, joule is not familiar. So we can use the term calorie as a measure for energy, as you learned from your video. So calories, or a calorie, is the energy needed to raise the temperature of 1 gram of water by 1 degree Celsius. So that's the definition of a calorie, the energy needed to raise the temperature of 1 gram of water by 1 degree Celsius. And keep in mind here that 1 gram of water is equal to 1 milliliter of water. Okay, so when you see this, we can use grams and milliliters when we're talking about water. Okay, and we can use grams and milliliters interchangeably. So a calorie is the energy needed to raise the temperature of 1 gram or 1 milliliter of water by 1 degree Celsius. And let's see, let me come up here. 1 calorie is equal to 4.184 joules. Okay, so 1 calorie is equal to 4.184 joules. The joule is a very small unit. So a lot of times you'll see joules expressed as kilojoules, because the joule is such a small unit. So 1 calorie is equal to 4.184 joules. All right. Now, a calorie is also a very tiny unit. So a calorie is a small unit. 1 calorie equal to 4.184 joules, joules being an even smaller unit than a calorie. So a lot of times we're going to not use little c calorie, we're going to use big C calorie. Okay, 1 big C calorie is equal to 1 kilo small c calorie. Okay, so that's 1,000 small c calories. Okay, so a big C calorie is equal to 1,000 small c calories. And as you learned from the video, what we see on nutrition labels as to the calories that are in food, those are actually big C calories. Okay, so if something has 100 calories as designated on a food label, that's actually the same as saying 100 times 1,000, which is equal to 100,000 little c calories. Okay, well, nobody wants to see that on a nutrition label, right? So we put everything in big C calories. And again, that is because the calorie is such a tiny unit. We're talking about the energy needed to raise 1 milliliter of water. And to give you a perspective on that, 1 milliliter is the amount that we put in one of those little pipettes when we're working in the chem lab, okay? So, and just the stem of the pipette, not even what fills the bulb of the pipette, it's the stem, 1 milliliter. So that's the amount of water we're talking about. And so a calorie is the amount of heat that is needed to raise the temperature of that tiny amount of water by 1 degree Celsius. So that's a tiny amount of energy. Okay, so the energy that's contained within food, okay, and that being potential energy, is a lot more than that. Okay, there's a lot more energy there in that food, and so that's why we use that big C calorie to represent that. All right, so let's look at a few more little definitions here, and then we're going to put all of this together. So when we look at energy, we look at the energy of a system versus the energy of its surroundings. All right, so the system is what we're actually studying. So this is the portion we single out for study. Versus the surroundings being everything else. Okay, so let's say I have a beaker here, okay, And so this is my beaker. And I've got some water in my beaker. Okay, so there's my water in my beaker. And it's sitting on a tabletop. Okay, so here's my tabletop that my beaker is sitting on. So my system that I am studying is here. Okay, what I'm looking at is what is happening with this water, because I'm going to put something in the water. I'm going to put some type of salt or something in the water. So let me show some little salt particles in here. Okay, so I'm going to put something in my water, and so this is going to be my system. This is what I'm going to actually study. Okay, everything else, so the tabletop, the air, okay, so all of the air floating around here, that's all my surroundings. Okay, so when we look at systems and surroundings, we have to consider what type of system do we have. Okay, so we can have an open system. And an open system is when both matter and energy can be exchanged with the surroundings. Okay, so this example that I've drawn here for you, this is an open system. Okay, I don't have a lid on top of my beaker here. All right, so I am exchanging matter. Okay, some of these water, especially when I'm heating this, some of these water molecules may be converted to gas and be exchanged with the surroundings. Some water molecules in the air may condense and come into my system. So what I've drawn here, this is an example of an open system. So this right here, this is an open system. I don't have anything that's separating my system from my surroundings. Okay, so this is an open system. Now, I can also have a closed system. Okay, so in a closed system, we have energy that can be exchanged. So we can exchange energy, but not matter, with my surroundings. Okay, so I can exchange energy, but not matter. So if I was to, let's say, put a lid or put a covering over my beaker here. So I'm just going to kind of shade this in so you can see that this is a covering. So I've got a lid, I've got a covering, I've got some type of material, maybe a piece of metal or a piece of plastic or something. So now I have a lid on my beaker. Now I have a closed system. Okay, so now this system becomes closed. I can still exchange energy with my surroundings, okay, because I may like have a flame here, or maybe this is hot water and it's going to cool off as I set it on my tabletop, because it's going to exchange energy with the surroundings. But no matter is going to be exchanged. Matter is not going to be able to get in or out because now I have a lid over my system. Okay, so that would be an example of a closed system. We can also have a third type of system called an isolated. Okay, and this is when neither matter nor energy can be exchanged with the surroundings. And this would be like something that would be taking place in a vacuum to get a true isolated system. The best thing that we can think of in terms of an isolated system that that you would be familiar with is what happens in like a thermos. Okay. If we have like a stainless steel thermos that we put coffee in, and we put hot coffee in it, that coffee is going to stay hot for a really, really long time. Now, it's not a true isolated system because eventually the coffee will cool down, but it's going to stay hot for many, many hours because no matter is being exchanged and very, very little energy is going to be exchanged. So that's about the closest to an isolated system that we can get outside of a vacuum where nothing is there. Okay, so system versus surroundings. The system is what we're singling out for study, and then the surroundings are everything else. So we can have open, closed, or isolated. Okay, how do we feel so far? Do you have any questions or any comments or anything so far? Or are we good? All right, I've got quite a few thumbs up. So we'll go ahead and continue on. Okay, so you've probably heard of thermodynamics before, and we have several laws of thermodynamics, basically the laws that regulate energy in nature. And for us, the important law of thermodynamics to consider is the first law of thermodynamics, which tells us that energy can be neither created nor destroyed. Okay, so energy can be neither created nor destroyed. In other words, energy is conserved. There's a finite amount of energy in the environment, and so what we do is we just convert it from one form to another. We conserve it and convert it from one form to another. So as an example of this, we can think about solar energy. All right, so we have energy from the sun. Plants have chloroplasts that allow them to absorb that energy from the sun, and they use that energy to make sugars. So that solar energy is then converted into chemical energy because it's going to be found within some type of chemical compound, sugar or starch. Okay, so then that becomes essentially potential energy for us. Kinetic energy for the plants, because they're going to use that energy that they have made. They're going to use that chemical energy in the form of sugar and convert it into ATP. Okay, they're going to convert it into some type of mechanical energy. And we're going to do the same thing when we eat the plants. Okay, so when we eat, the vegetables or the fruits or the starches, the potatoes and things like that, we now have consumed those chemical compounds, and when we digest those, then we are going to now have that energy, that's chemical energy, that we can use for our cells to do work. So we didn't create energy. We didn't destroy energy. It just changed forms. We went from solar energy to chemical and mechanical energy within a plant to chemical and mechanical energy within our bodies. So that's the first law of thermodynamics, that energy cannot be created or destroyed. It's just going to be conserved. It's going to be changing forms. And so we have an equation that we can use for that. Oops. Okay, so we can have delta E. So this triangle here, okay, and we're going to use a lot of triangles in this chapter. This is the Greek letter delta, and it refers to a change. Okay, so delta, this triangle is the Greek letter delta, and so we read that as delta. So this would be delta E is how we would read that. Okay, so delta E, where E is energy. Okay, is equal to Q plus W. Okay, Q is heat and W is work. Okay, remember we said before that our definition was, or a definition of energy was the capacity to do work or transfer heat. So when we look at the change in the energy of a system, we're going to look at what's happening to the heat and is there work being done on the system or by the system. So our change in energy, our delta E, is equal to Q plus W. Okay, so let's look at some applications of that. When heat, okay, and that's Q, so when heat is added to a system, or work, that's our W, is done on a system, energy is increased. Okay, and again, keep in mind our formula. Okay, so if we add heat, or if we do work on a system, then energy is going to go up. So our change in energy, our delta E, is going to be a positive change. Okay, so if heat is added or work is done, then we're going to get a positive delta E, okay, because energy is going to go up. When heat is transferred from the system, and when we say is transferred, we're from the system, we're saying, or we're kind of understood that to be, it's going from the system to the surroundings, or work is done by a system. So the system is actually doing work. Then energy is going to decrease, because now, if we look at our formula, if energy is moved, if heat is leaving the system, or if work is being done by the system, okay, then we get a negative delta E. Our energy increases. That's not saying we have negative or positive energy, okay, and that's not saying that we're gaining or losing energy. Remember, we can't create or destroy energy. What we're saying here is that energy is being added to the system, so the energy of that system can increase, or energy is, or work is being done by the system, then energy of that system is going to decrease. Okay. So if we look at that another way, because we're going to be mostly concerned with heat. Okay, so let me write my formula again. Okay. When heat, so let's just look specifically at heat. When heat is transferred to the system from the surroundings, Q is positive. When heat is transferred to the surroundings from the system, Q is negative. So it really doesn't matter if work is being done on the system or by the system at this point, because we can just look at heat. So when heat is transferred to the system from the surroundings, Q is positive. Okay. And when heat is transferred to the surroundings from the system, Q is negative. Okay, so if we think about an example of this, okay, so let's look at an example. Okay, let's look at an example. Let me call this scenario 1 and scenario 2. So let's look at an example of 1. Boiling water. When we boil water, heat is transferred to the system from the surroundings. Okay, so our system is going to be our pot of water, and our surroundings would be the burner on the stove. Okay, so when we boil water, we are transferring heat into our system. So Q is going to be positive because we are moving heat into the system, and we can measure that. We can measure that with the temperature. If we put a thermometer in our pot of boiling water, the temperature is going to start to increase. Okay, so our delta E, our change in energy, is going to go up. We are adding energy to the system. Okay. If we look at an example of 2, heat is transferred to the surroundings from the system, we can look at freezing water. So we have our room temp water, our tap water, temperature water, about 25 degrees Celsius, 30 degrees Celsius, something like that. And when we put it in the freezer, heat is going to be transferred from the water into its surroundings. Okay, so it's going to be transferred from our system, our little tray of ice cubes, that would be our tray of water to make ice cubes, would be our system, and the surroundings would be the freezer. So the heat is being transferred to the freezer from the water in our ice trays. And so Q would be negative. We are essentially decreasing our amount of energy. So in a process in which the system absorbs heat, like we've got in 1 where Q is positive, that is called an endothermic reaction. Okay, so the system is going to absorb heat from its surroundings. That is an endothermic reaction. And in scenario 2 here, when heat exits out of the system into the surroundings, like when we're, freezing water, that is referred to as an exothermic reaction because heat is being given off by the system. And I'm using water here as an example, and you wouldn't normally think of freezing water as being an exothermic reaction, but it is giving off heat to its surroundings. Typically, when we think of an exothermic reaction, we think of flames. We think of, putting like pure sodium in water, and we get flames and these reactions that occur. But we don't have to have all those little fireworks to get an exothermic reaction. And a lot of times students kind of get these confused because you think, okay, if I'm boiling water, that water is getting hot. And I think of an exothermic reaction as something that's getting hot. But that's not the case. You will, you'll see as we kind of go through this and look at some more examples, and as we look at the lab, when the system absorbs heat from its surroundings, and that means it's taking in heat. And we think of endotherm, we think of inside heat. So it's taking heat from the surroundings into the system. And then in your book kind of gives you an example, heat flowing into the system from its surroundings. And in another example, let me go to another page and kind of give you another example. So another example of an endothermic reaction. So, and I think this may help make it a little bit more sense. So another example of an endothermic would be melting ice. So if you leave a piece of ice out on your counter, okay, it's going to absorb energy. So that ice absorbs energy from its surroundings. And we don't necessarily have to add any heat to it through a flame or anything like that. Just the room temperature air is going to be warmer than that ice. And so ice is absorbing energy from its surroundings, from the countertop, for instance. If we touch that container, it's going to feel cold to us because heat is passing from our hand to the container. So an endothermic reaction, if we were to touch that, a lot of times, not all the time, but a lot of the times it's going to feel cold because heat is leaving our hand and going to the container because the container is colder than our hand. And so we're going to feel that as cold. Okay. And then kind of the converse, exo, when something is giving off heat, it's going to feel hot to us. Okay, because now the heat is passing from the container to our hand. Okay, and so that would be an exothermic reaction. All right, table 5.1 on page 173 kind of help with that. Okay, so another term that we have to get through is enthalpy. And enthalpy is a state function. And when we say a state function, what we're talking about here is it gives the state of the system. So basically, it's a property of the system determined by specifying the system's condition or state. So when we say it's a state function, we're going to be looking at temperature, pressure, volume, something along those lines. So it's a state function that relates mainly to heat flow. So basically, it's a state function, so giving us kind of the state of our system that really deals more with heat. Okay, and our equation for this is H here. H is enthalpy. Remember, we use Q for heat. So H is enthalpy. E, remember, is energy. P is pressure. And V, volume. And a lot of times we'll see this stated as delta H equals delta E plus P delta V. Okay, so delta H, so a change in enthalpy is equal to a change in energy plus pressure and a change in volume. Pressure, notice we don't have a delta pressure. We don't have a delta P because pressure remains constant because we're dealing with atmospheric pressure. Remember, that's the pressure that is pushing down on us from the atmosphere, from all of the gases in the atmosphere. And so as long as we remain in a constant place, then we're going to have constant atmospheric pressure. So our pressure is not going to change. If we change our volume, we change our energy, then we change our enthalpy. We're changing how heat is flowing through a system. Okay, that's really what we're looking at with enthalpy, is how is that heat flowing through a system. If we change the amount of volume, if we change the amount of energy, then we're going to change the enthalpy. What we mainly use this for is to look at what is happening in a chemical reaction. So we use what we call the enthalpies of reaction, where we have delta H, so a change in enthalpy of our reaction is equal to the enthalpy of our products minus the enthalpy of our reactants. Okay, and so an example of this would be H2 gas plus O2 gas yields 2H2O gas, and we would see this delta H out here equals negative 483.6 joules. Okay, so this right here, this little thing that I've written out right here, this whole thing is referred to as a thermochemical reaction. Okay, because we've got our reaction, we've got our balanced reaction here, but then we've got this delta H, we've got this enthalpy change out here of negative 483.6 joules. So this tells us this is the enthalpy change in our reaction. We've taken the enthalpy of our products and subtracted out the enthalpy of our reactants, our H2 and our O2, and we can measure that. And that is equal to negative 483.6 joules. When delta H, let me find a place to write this. When delta H is negative, that is an exothermic reaction. So this gives off heat. When delta H is positive, we have an endothermic, meaning we had to put in heat. Okay. So if delta H is negative, that is exothermic. If delta H is positive, that is endothermic. So this reaction, when we combine hydrogen gas and oxygen gas to get steam, we have to, or that's going to give off heat. That's why the water there is a gas instead of a liquid, because we're dealing with steam instead of liquid water. So we're going to get these thermochemical reactions, and we can calculate this. Given a few pieces of information, we can calculate the enthalpies of reaction. Okay, now we're going to be given the information that we need to work these. So let's look at 5.5 on page 180. Okay, so they give us, or they want to know how much heat is released. So we're looking at how much Q is released if we burn 4.50 grams of methane gas in a constant pressure system. Okay, remember that our enthalpy formula depended on constant pressure. Okay, so we want to know how much heat is released when we burn 4.50 grams of CH4. Now, let me go back to my previous slide. When we talk about how much heat here, when we're saying how much heat is released, we're looking at energy. We're talking about heat because we know that it's going to be giving off heat, but we're looking for a unit in joules. So don't be confused, okay? On this type of problem, when they ask you how much heat is released and they give you a thermochemical reaction, you're going to be looking for an answer in joules. Okay, so your answer is going to be in joules. And they tell me to look at the equation 5.18, which is at the top of page 180, where I have CH4 plus 2O2. This is a standard combustion reaction. Remember, combustion reactions, and this is why we went over combustion reactions in anticipation of thermochemistry. Remember, a combustion reaction is when we take a hydrocarbon, we add oxygen with it, and we get carbon dioxide and water. So I'm going to have CO2 gas plus H2O liquid. And the difference that we're going to see here is our delta H at the end. So delta H is equal to negative 890 kilojoules. So your answer can be in joules, I guess I should say, or kilojoules. Okay, but joule is going to be a part of your answer. Okay, so they want to know how much heat is released when we start with 4.50 grams of methane. This is the heat that is released, okay, and it's negative, so I know it's exothermic, so this is the heat released from this equation. But we want to know how much is released specifically when we have 4.50 grams of methane. So we start with what we know. And we're going to have to set up some unit conversions here. All right, so I need y'all to remember back to when we first started talking about chemical equations. And I know that's been a while. When we first started talking about chemical reactions, and we talked about how to balance those and what those coefficients meant. Remember that coefficients refer to the number of moles of each of those components that we have. And that if there isn't a coefficient, we understand that to be 1 mole. Okay? So I have 1 mole of methane gas, 2 moles of oxygen gas, 1 mole of carbon dioxide gas, and 1 mole of water. Okay? And when I put 1 mole of methane with 2 moles of oxygen gas, and I get 1 mole of carbon dioxide and 1 mole of water, that produces 890 kilojoules of heat. Okay? That's the amount in 1 mole, or for 1 mole of methane. But I'm given grams. So how do I convert grams to moles? What do I use? Yes, Michelle, both of you. Yes, molar mass. So don't be confused when you see this problem. Okay? Think, oh gosh, I've got grams. I don't even know what I'm going to do. I'm going to use the molar mass. And the molar mass of methane is 16.04 grams. And that's the amount in 1 mole of CH4. Okay? Now, let's look at my reaction. Okay? I know in order to cancel things out, I've got to put mole of CH4 on the bottom, and I've told you my answer is going to be in joules or kilojoules. Since I've got kilojoules here, then I know I've got to have kilojoules at the top. So my grams already cancel out. I've got to get my moles to cancel out. So I go back to my chemical reaction, and I see that my coefficient is 1. So 1 mole of CH4 produces negative 890 kilojoules. Okay, so I'm going to get my molar mass here. That's going to be my first step. And then I'm going to look at my thermochemical reaction here. So I'm going to get this information from my reaction. If I had 17 moles that produced a negative 890 kilojoules, then I would put 17 here. Okay, so this number that I get right here is going to come directly from my chemical equation. All right, so now I just plug it in. I'm going to say 4.50 times negative 890 divided by 16.04, and I get negative 250 kilojoules. So if I combine 4.50 grams of methane in this combustion reaction, then that's going to release 250 kilojoules of energy. Okay, remember it's negative because it's an exothermic, so it's releasing that into its environment. Now, look at this and see, does this answer make sense? Yes, it does. Okay, and here's how I know that this answer makes sense. I have 4.50 grams, which is not a mole. A mole of methane is equal to 16.04 grams. I know that from my molar mass. So since I'm not using a whole mole of methane, then I would expect my answer to be less than my delta H I was given in my problem. And if I look, I see, oh, that's about a fourth, roughly a fourth, and my answer, 250, is a little bit more than a fourth of my 890. So yes, this answer makes sense. Okay. So let's look at another one of those. The top of page 181, we'll do this practice exercise. And again, they want to know what is the enthalpy change. Okay, and that's another way that they can word this. So they can say what is, they can say how much heat is released, or what is the enthalpy change. Both of those are the same thing in this context. Okay, in this context, they're both the same thing. So our answer is going to be in joules or kilojoules. And they give us our equation. We've got some ethanol. Okay. And this is another combustion reaction. We're going to combine that with oxygen. And we're going to get 2 moles of carbon dioxide and 3 of water. And I don't have room up there, but they tell me normally that would all be written on the same line, but I don't have room there. So again, this is an exothermic reaction because I've got a negative value there, and it's negative 555 kilojoules. And they want to know my change in enthalpy when I have 15 grams of ethanol. So I'm going to work this the same way. I'm going to start with what I know. And they were nice enough to give me my formula weight, which is the same as my molar mass in my problem, 46 grams per mole. And I'm going to go to my chemical reaction. I see I don't have a coefficient there, so I understand that to be 1. And I'm looking for my answer in kilojoules, so I just plug in what they told me was my delta H for my entire reaction. My moles cancel, my grams cancel, and when I work this, I end up with a negative 181 kilojoules, which is answer B. Now, I'm going to, again, look and see, does this make sense? Well, 15 is less than my molar mass of ethanol. It's about a third of my molar mass of ethanol, and my answer is about a third. 181 is about a third of 555. So yes, my answer makes sense. So if I combust 15 grams of ethanol, then I end up with negative 181 kilojoules that are being released, okay, because that's an exothermic reaction, okay. Now getting to the fun stuff of this chapter with calorimetry. So how do we measure all this stuff? Well, we use calorimetry. So calorimetry is a measure of heat flow. And we measure this using what we call a calorimeter. Okay, so this is our device that we use. Okay, so the more heat an object gains, the hotter it gets. We all agree with that? The more heat an object gains, the hotter it gets. We can measure that with the temperature or with the thermometer, right? So when we look at different objects, the magnitude of our temperature change, which we indicate with delta T, remember delta indicates change, T we're going to use to represent temperature, so the magnitude of our delta T varies from subject to subject, or from object to object, substance to substance. Some substances can gain heat faster than other substances. Okay, and so the magnitude of our temperature change is going to vary, and that is referred to as the heat capacity. Uh-oh, hang on just a second. Let me pause this. Okay, had to take care of that. Hang up that phone call. Okay, so heat capacity is the delta T, so the change in temperature experienced by an object when it absorbs a certain amount of heat. Okay, so the heat capacity is the change in temperature, the delta T, experienced by an object when it absorbs a certain amount of heat. And how much is that amount of heat? Well, it is the amount of heat required to raise the temperature of that substance by 1 degree. And we're talking here 1 degree Celsius or 1 Kelvin. Remember, those are both on a 1-to-1 point scale. And so we can use Kelvin or you can use Celsius most of the time. What I'm going to do and what you're going to see is we're going to use degrees Celsius as our unit for this. And we represent heat capacity with a capital C. And so we can have C sub M, which is our molar heat capacity. So this is the amount for an entire mole of a substance. Okay, so that is the heat capacity of 1 mole. Or we can have the specific heat capacity, which is the heat capacity of 1 gram. Okay. Most of the time, you are going to see specific heat capacity referred to as just specific heat. They leave that off of there, so I'm going to kind of highlight that. And you often see it as just C without the sub S. Okay, so we're going to use C to represent specific heat, and we know that we're talking about the heat capacity of 1 gram of that substance. These are constants. These have been measured, and we can go to a table or we can go to the internet and we can look up the specific heat of pretty much any substance we want to. Okay. So we can look that up. Those are constants. Those are things that we can find and plug in. Okay. So our specific heat, okay, so again, I'm going to use just big C, is equal to Q divided by M delta T. Okay. So specific heat is equal to quantity of heat transferred, so our quantity of heat, our Q, divided by the mass of our substance times the change in temperature. Okay, so specific heat is equal to the quantity of heat, Q, divided by the mass times the change in temperature. Okay. For instance, the specific heat of water, so our specific heat of water is equal to 4.18 joule per gram Kelvin or Celsius. I like using Celsius. That's what I'm familiar with. And your book uses these interchangeably. You can put gram times degrees Celsius or grams times Kelvin. It doesn't really matter. So that's our specific heat of water, 4.18 joules divided by gram times Celsius. Okay. Now we can rework this equation because we don't need to calculate the specific heat. It's already been done for us. So as you saw in your video that you watched, we can rearrange this equation to get Q equal to, and your book kind of rearranges a little bit. I like doing it like this so that it kind of looks like MCAT, as you saw in the video. Helps you kind of remember that a little bit easier, that Q, our quantity of heat, is equal to our mass times our specific heat times our change in temperature. So mass times specific heat times temperature change. Okay. So MCAT. All right. So we can, if we are given the mass of a substance and we are given its initial temperature and its final temperature, if we're given the amount of temperature change it has, we know our specific heat is a constant. We can look that up. Then we can calculate how much heat is going to be transferred. Okay. So if we look at 5.6 on page 183, we want to know how much heat, so that's our quantity of heat, Q, is needed to warm 250 grams of water from 22 degrees Celsius to 98 degrees Celsius. So we have our temperature, we have our mass, we know our specific heat. I can look that up, and I know my specific heat of water is 5.18 joule divided by gram Celsius. Then I can plug it in. So the first thing I've got to do is get my delta T. Remember, it's not just T, it's not just temperature, it's delta T. So I take my final temperature, which was 98 degrees Celsius, and I subtract my initial temperature, which was 22 degrees Celsius, and I get 76 degrees Celsius. Notice that number is positive. Okay. So this is going to be an endothermic. My reaction says how much heat is needed to warm. So I'm going to have to add heat to my system. So it's going to be positive. So now I've got my delta T, I've got my C, I've got my mass, 250 grams. So now I'm ready to plug it in. Q is equal to M, my mass, 250 grams, times C, my specific heat, 4.18 joule per gram degree Celsius, times my delta T, 76 degrees Celsius. So notice what's going to happen here. My degrees Celsius cancel because this is on the bottom. Okay, it's joule per gram times degrees Celsius. So my degrees Celsius cancel. My grams cancel. I'm left with joules, which is my unit for Q. Okay, so I just just multiply all these together. 250 times 4.18 times 76 gives me 79420 joules. Okay. Now I can put that in kilojoules. If I divide that by 1,000, then I can put that in kilojoules if I want to. Okay. And that just involves moving the decimal. So it would be 79.42 kilojoules. I have two significant digits, so I can say 79 kilojoules. Or I can leave that in joules, but I have to get rid of some of these numbers. So I can say, the pen keeps leaving me, 79,000 joules. Okay, either way is fine. Or you can put it in scientific notation. 7.9 times 10 to the 4 joules. Doesn't really matter to me which one. The most important thing to remember is put your units, whether I know you're dealing with kilojoules or joules. Because if you just put 79,000, maybe you didn't work this problem right. I don't know. Did you put that in joules? Or if you just put 79 without anything, I guess if you just put 79,000, I'd realize it was in joules. But if you just put 79, well, oh, goodness, this isn't worked correctly. So make sure you always include your unit on there, okay? Now, the question then asked, what is the molar heat capacity? So we have this, but we want to know the molar heat capacity. So how much would it take, not for 250 grams, but for a mole of water? Okay, and so if they want to know molar heat capacity, so that's our C sub M, all we do is take our specific heat capacity, our C, or C sub S, or just C, okay, times our molar mass. Okay, so Cm would be equal to 4.18 joule per gram times degree Celsius times our molar mass of water, which is 18.02 grams. Okay, and that's the amount in 1 mole. So my grams are going to cancel, and I'm going to multiply 4.18 times 18.02, and I get 75.3. And my unit here is joule, this time mole degrees Celsius, because I've exchanged grams for moles. So my unit on molar heat capacity is going to be joule per mole degrees Celsius. Okay. So that's my molar heat capacity of water. My specific heat capacity, the amount that it of energy for 1 gram is 4.18. But if I have a whole mole, it's going to require 75.3. Excuse me, 75.3 joules per mole degree Celsius. Okay. So those are our formulas that we can use to figure out how much heat is needed. So last thing here is we can use the calorimeters to measure all of this. Okay, and so we have two types of calorimetry or calorimeters. We have constant pressure calorimetry, okay, which is what's occurring at atmospheric pressure. Okay, again, it's constant pressure because it's due to the atmospheric pressure. And this is typically going to be some type of, a lot of times we'll use an open system for this. Occasionally we can use a closed system, but we call this coffee cup calorimetry. or we use a coffee cup calorimeter. And one of these is shown for you at the bottom of page 183, and that's what we're going to use for the lab. Is I'm just going to use 2 coffee cups, 2 plain Jane styrofoam coffee cups, and I'm going to use 2 to make it a little bit more insulated. And I'm going to have a reaction that takes place within my 2 coffee cups, and I'm going to measure the temperature change, but that's constant pressure calorimetry. And this is the easiest type of calorimetry you can do. No, it's not going to be exact because I'm still going to have some heat loss to my surroundings, but it's going to be pretty darn close. Okay. I can also have constant volume calorimetry. Okay. Constant volume calorimetry. And this involves a device that we call a bomb calorimeter. And one of these is shown for you on page 185. Okay, a bomb calorimeter on page 185. And this is what happens. This is the, these are combustion reactions. Basically, what we do when we were just looking at all those combustion reactions, those are performed in a bomb calorimeter. We have to be able to control the volume to be able to have our volume constant, because these are going to be such extreme exothermic reactions that we're not going to get accurate measurements. And so we perform these in what we call a bomb or a reaction chamber. And these are going to be used, this bomb is an insulated, sealed vessel. So it would be like taking our coffee cup calorimeter and putting it in a thermos, for instance. Only it would be a thermos that had a hole in the top for a thermometer and a stirrer and an ignition source. So we can get a true measurement of the energy that is in those reactions. All right, so that's what I have for thermochemistry. So do we have any questions about any of these calculations or anything like that? All right, so I'm going to save that for us. Miguel has a question. Yes. Okay, I can't get there to y'all. What's going on? There we go. Can I work out the Ed puzzle problem for specific heat? Yes. Calculate the amount of heat released. Hold on, let me write that down. Give me a second, let me write it down, and then yes, I will do that. Okay, let me get my whiteboard back up, and then I can do that. Let's see. Make sure y'all can see that. Okay. So, I want to know Q in calories. So this time they don't want joule, they want calories. And I have 7.4 grams of water, and it cools 4 from 49 degrees Celsius to 28 degrees Celsius. So remember, my formula is going to be Q equals mass times specific heat times delta T. Now this time, the first thing I'm going to do is get my delta T, and I'm going to say final minus initial. This time, my number is going to be negative. My delta T is negative because I'm cooling. I'm not adding heat. I'm essentially losing heat to my surroundings. So I'm going to say my final temperature, which is 28, minus my initial temperature, which is 49. Delta T is a negative number. So that's going to be negative 21 degrees Celsius. So now I'm going to say my mass, 7.40 grams. My specific heat is 4.18 joule per gram. Oops. Joule times degrees Celsius. And I've got negative 21 degrees Celsius. So my grams and my degrees Celsius cancel. So I'm going to say 7.4 times 4.18 times negative 21, and I get negative 649.572 joules. But they wanted my answer in calories. And remember, 1 calorie is equal to 4. Let me find my notes. 184 or 182? 184. Okay. I'm going to make sure. So 1 calorie is equal to 4.184 joules. So I'm going to take this amount and I'm going to say 1 calorie is equal to 4.184 joules. So essentially I'm just going to divide. And when I do that, I get negative 155.25 calories. And was it little c calorie? I don't have that question in front of me. Yes, okay. So then I'm going to use significant figures. I've got 3 significant figures in my 7.40 grams. And so I'm going to say negative 155. Sometimes when you're working these, temperature is not used. Sometimes temperature is not included in the significant digits, but if it is, it could be negative 160. So that we have 2 significant digits. So Ed Puzzle has the wrong, so could 1 calorie be? You could put your conversion there, but you would have to actually do the conversion in your constant. It's best, Kinley, to it's best to leave the joules in there and work it out as joules and then convert it to calories at the end. So Ed Puzzle has the wrong answer. Okay, I'll 1 calories. Okay, hang on, let me take a look at it. I'm taking a look at the video. Give me just a second. Okay, I figured it out. I understand. I watched that part of the video and then I continued watching. So the problem, okay, so what we worked out here is on the Ed puzzle as well. At the end, when it asked for the amount of calories, so we worked out the problem correct. So now I understand what problem you are talking about. It took me a minute to find it. So the question asked, before we worked anything out, it asked you for the temperature change, and then it said how many calories of heat would be released in this example. Remember that 1 calorie will raise the temperature of 1 gram of water by 1 degree Celsius. So they're asking here in this example, not for the, and this was worded wrong, and I should have worded this differently. They're just looking at when 21 degrees are released, how much heat is released? 21 calories. So I'm not looking at this specific example where there are 7.40 grams of water, just in general. And that's where I should have said in general instead of in this example. I just wanted you to relate that you had a temperature change of 21 degrees Celsius, so you would have 21 calories released. So that's why that one is wrong, and I'll go back and I'll adjust that for you because that was my fault. Because looking at the scores on that, some of you got that one right, but a lot of you put the answer 154.4 calories, which is what we got when we worked that out in calories, but that was specific for 7.40 grams. Okay, so in general, and that's where I messed up, if we have a temperature change of 21 degrees, like we did in this problem, then we would release 21 calories of heat. So I understand the confusion about that. I'm sorry. That is my wording on that one, and I will fix that. I will adjust that. For those of you that got the 154, I'll fix it. But that was my fault. That was the way I worded that question a little bit wrong, and that was my fault. So yeah, I'll go in there and fix those. So if you put 154, then you're going to get that right, because you did work the problem and you converted it to 154. That is specific for 7.40 grams of water. But in general, if we have a temperature change of 21 degrees Celsius, then we have 21 calories of heat that is released. All right, other questions? No other questions? I want to make sure, because I know there's a lot of math in this one. All right, so before you all sign off, I want to take a look at your group assignment with you. So give me just a second to get my to get y'all's attendance written down here, and then we'll go over to Blackboard and I'll show you your assignment. Okay. So let me close this down, and I will upload your notes like I have been. So you'll have those. I've already saved those, and I'll upload them as soon as we're finished here. But let me get over so that I can share my screen in Blackboard so I can show you this. Okay, hopefully when I go to share my tab, it won't shut down Chrome, but it's happened several times. So if it does, just give me a second and I'll come back. Oh, yay. Okay, it worked this time. Okay, so in your April online activities folder, you've got this assignment, Thermochemistry Infographic, okay? And you're going to work with your assigned group to complete this assignment. And when you submit this, so each person in the group will submit the same thing, but I want you to include how each member contributed. So if, you know, one person contributed the graphics and one person plugged everything into the computer program, I want to know what each person did. I'm going to explain in just a second, Xavier. So I want to know what each member did. And if you have a group member that did not do anything, I want you to tell me that that group member did not do anything. Okay. So what you're going to do is create an infographic on thermochemistry. And I'm going to pull this up for you. Pull up these directions so you can see this. Okay, so while that's loading, you're going to notice a new tab over on your navigation panel over here that says groups. Okay, so you're going to go to your groups, and I have 3 groups. Now, in your view, it may only show up the group that you're a part of. I don't know, because since I'm not a student, I can't see what shows up when you log in as a student. So it may have all 3 groups here. It may have just your group. But when you get into your group, you'll see the members of each group, and then you'll see your tools. So y'all can communicate through Collaborate. You can send email just to your group. You can set up a group discussion board. And I have this set up where anybody in the group can set up a discussion board and y'all can communicate through the discussion board. I also have this file exchange where as you're working on it, if you need to send files to one another, you can do that here. So your group members are all listed there. I've got 3 different groups instead of being in 5 like we do in class, or 4. No, 5. I just did 3 groups of 6 each. And so you'll be able to communicate with each other that way. So you'll just use this groups tab over here that I added on your navigation bar. If you get in there and it's not working, you're not able to see your group, please let me know, because like I said, this is the first time I've ever done this and used this. And so I watched some video tutorials and went to the Blackboard help, and I think I've got it all set up correctly, but let me know if it doesn't work. So let me show you your assignment right quick. So you're going to create a thermochemistry infographic. I don't know why that's not sharing. Let me try again. I don't know why it's not sharing. There we go. Okay. So you're going to select some type of real world application where you've got some form of temperature regulation. Okay. And I've got an example on the second page of body temperature regulation. You can't use this one. Okay. But you can use any other type of system or application where there's some form of temperature regulation. So it could be any type of, like appliance. Okay, it could be an engine. It could be, they give you an example here, an ice hockey rink. It could be plants. Okay, because they absorb heat, solar energy from the sun. So any real world application where there is some form of temperature flow. And you're going to create this infographic and you're going to answer these questions. Okay, so you're going to answer these 6 types of questions, and you're going to do, you should have pictures and diagrams. There are several different websites here that allow you to plug in your information and move it around so that you can put in your graphics and put in your information. Okay, this one created by Vengage, and then you can save that as a JPEG or a PDF. And so that's what you'll turn in. And each group member should turn in the same infographic. Okay. I don't necessarily want to see these questions show up on the infographic. If you look at this example, they're not putting those questions on there. They're answering them. They're putting the correct information on there, but not just strictly answering the questions. Okay, they're talking about what happens and then relating that to thermochemistry. And I want to see some images or some pictures on here as well. And you'll put your group names on there. And so what you'll turn in is your infographic. Okay, so you'll turn in this part of it with your actual infographic. And you'll tell me in your assignment, and I've got it set up as an assignment submission, so you'll upload your infographic as an attachment, and then in the body of it, of the text there, you'll tell me who did what. Okay, so you'll have each group member and you'll say, well, so-and-so answered questions 1 through 3, and so-and-so answered questions 4 through 6, and then so-and-so took all of that information and put it into the infographic. So-and-so found all the pictures. So however you want to break up the workload, again, this is up to you, just like when we work on any other type of group project in the classroom. But I do want to see all members participating. Okay. That's the big thing. And that's why I want to know who did what, because I want to make sure that everyone is participating in their groups. Okay, this is due next Friday at 11:59, so you've got a little over a week to work on this. We won't have a class meeting on Tuesday because you'll have lab 9, your thermochemistry lab, using our coffee cup calorimeters, and I will post this like I did the others. I'll include the PowerPoint, but I'll also include the YouTube links to the specific videos if it's easier for you to get on YouTube and look at those. So all of your images and videos will be in the PowerPoint, and then I'll send you the link to the videos. There'll be a couple of videos. They'll be shorter. Most of what happens you can't really see. It's not like observing those chemical reactions like we had last time, and so you can't really see it very well. Most of what you'll have are pictures, and then you'll put all of that in the data table. And what you're going to be doing is you're going to be looking at 2 different reactions that take place. One is endothermic, one is exothermic, and you're going to be calculating the amount of heat that is absorbed or released based on the data that you get. And so you'll have a data table, and then you'll have some questions that you'll answer afterwards. So I'll have that hopefully up there for you today, but if not today, it will be up by Monday. But your thermochemistry infographic is already up there. You can go ahead and start working on that today if you want to. So, all right. Any questions? Yes, Lauren. I just want you to tell me what you would do. Let me look at that again. Let me go to that page. Hang on just a second. Okay, so you're looking at these 3 unlabeled bottles, and you want to design some experiments. So what you're going to do is you're going to look at the characteristics of those 3 substances: sodium sulfide, sodium bicarbonate, and sodium chloride. So you can do some experiments that look at their physical properties, like their melting points or solubilities or something like that, and design some experiments. So basically you would tell me, well, sodium chloride dissolves in water, so I will look at the solubilities of these. And you would tell me what you would do. I would measure out so many grams and put it in 100 milliliters of water. Okay, so you could do that. Or you could use the chemical reactivity. So you would look at each one of these and determine, can any of them act as an acid? Can any of them act as a base? Okay, well, we know that sodium bicarbonate can act as a base. So I can say, well, I know that sodium bicarbonate can act as a base. So I'm going to take so many grams of sodium bicarbonate, and I'm going to mix that with so many milliliters of acetic acid. And if I get a reaction, or I'm going to take 5 grams of my unknown powder and mix that with 5 milliliters of acetic acid. If I get a reaction, that I know it has to be sodium bicarbonate, because sodium chloride and sodium sulfite don't act as bases. So that's what you're going to do. You're either going to look at their physical properties, or you're going to look at the chemical reactivity, and you're going to have to find something that distinguishes them from one another. Okay, so what distinguishes sodium chloride from the other 2? What distinguishes sodium bicarbonate? What distinguishes sodium sulfide? So you can, again, look at physical properties or chemical properties of those. Yep. All right, any other questions? Okay, one other thing I want to add. Like I told you, I put zeros in the grade book for the things that I did not have. So get in that grade book and look and see. Some of you did not turn in your Unit 3 assessment. Some of you have not turned in your Unit 2 assessment. Some of you have not turned in some of the pre-labs that were past due, not just for 7 and 8, but for 1 through 6 as well. There wasn't one for 5, but 1 through 4 and 6. And then some of you have still not done the balloon stoichiometry and the stoichiometry problems and the chemical reactions worksheet and your lab 7 and your lab 8. I want you to get in there and get those done. As long as I have them by Sunday night at 11:59, I will not count them as late. But if they're submitted anytime on Monday and from then on, I'm going to consider them late. So get in there and get those done before you get too far behind and can't catch up. Okay. The other thing is that there were a couple of you that had some submissions in progress and nothing ever actually submitted. And so I'll be sending you an email with those. And then for those paper assignments, like I mentioned the other day, those paper assignments that I don't have, I'm going to be sending you an email with that, and I'll do all that today. So I'll be looking for an email from me today, and if you're missing anything, try to get those in, as quickly as possible, okay? All right, if y'all don't have anything else, then I don't either. So y'all have a good weekend. Enjoy your Easter. I know in DeQueen, if you have any, kids or nieces or nephews in DeQueen, we're doing a drive-by Easter egg hunt where people are going to hang up Easter eggs in their windows and allow people to drive by and look for the Easter eggs. So you may want to get out and do that. Just, stay in your vehicles, of course. But enjoy your Easter weekend. And again, we won't have a class session on Tuesday. So I'll see you back here on Thursday when we start on the gases, and I'll send out that link Thursday morning. So y'all have a good weekend, and I will talk with you next week.